Today's first speaker is OReilly, who's a principal research scientist at MIT Computer Science and AI. She leads the Evolutionary Design and Operation group there. She obtained her PhD from Carleton University. And today's talk is NIT, Integrating Large-Scale Partial Cognitive Analysis of Data.
Okay, well, thank you very much for coming to the last session and sticking with me. This work is co-authored with a postdoc in my group, Kalyan Machinini, who really should be the presenter, but is not. And let me start with an example of the problem. And I'm going to work left to right on this slide. We assume that there's this very, very large data set. I'm showing you here a set of images that perhaps could be on Flickr, but it could just as easily be a multimodal set of text and images and auditory signals, or it could be compiled astronomy observational data. And what we're interested in is deriving a clustering on this very, very large data set where we know what, with respect to the subjective bias of a targeted group of people who are going to look at it and judge and tell us those clusterings. Right? However, our problem is that no one person can cluster all this data, and we certainly can't ask all the people to cluster the data. So our strategy is going to be to partition the data into overlapping subsets and give a particular subset to each one of our assessors in this targeted demographic who's going to provide the clustering for us. Then we need to collect up all these partial subset groupings or subset clusterings and resolve them and fuse them or knit them together into a clustering that reflects the consensus of this particular population. And when I say reflecting the consensus, what I want to imply there is that that consensus clustering should reflect the agreement amongst the people, and it should discount the outliers in that population group. Right? Now, I still have a problem, which is if I have a very large data set and I really haven't told my assessors very much, I'm allowing them to take all their domain knowledge and their expertise and bring it to bear to decide how to group the data, then they could actually give me data and I can fuse it into a consensus clustering, but if I rearrange the data and I send it back, I could get a different consensus clustering. So I need to iterate in this problem until I achieve a stable consensus clustering. Right? And that's when, regardless of how much more data I present to these assessors in these subsets, the actual consensus clustering I've now adapted and updated is not going to change. Okay? So that's the problem. We call it NIT. We've also called it resolving subset groupings. There's a version of it that appeared at NIT in 2011 called crowd clustering, and that's way sexier. I really wish we picked it. Their particular instance is a little bit different, but you can see that there's different versions of this problem. Even just, for example, I could actually have this data distributed. And if this data was distributed, then there might be constraints on who could see what. And that would change the way in which I iterate and choose subsets for presentation, and it would change the efficiency of the iteration in terms of the convergence to something stable. All right? So that's the intuition behind the problem, and the way I'm going to proceed is to just present some terminology and formalizations, show you how we solved it, and then we created some synthetic data, a very small set, because of the origins with which we've been working on the problem, and I'll show you an empirical evaluation of the various strategies for iterating. So this is the same picture, but I've just iconized states, and I've got my data set labeled D. Its size is N. And that's very, very much larger than the size M of the subsets that I'm going to present to my assessors, which I label A, sub I, and I've got each of those. And we can assume that there's some ground truth clustering of the data, pi g, and assessors add some sort of noise to that because they all have their own subjective bias, right? And even that particular ground truth could be quite confused, and there would be this ability to cluster it differently just on the fact that things are similar in different ways, right? The bases of similarity are different. I'm going to call the clustering that each assessor gives me. There's a note with C, and I can actually encode that as a co-occurrence matrix. You know, it's going to be M by M for every element that the the assessor has seen, and it's going to have a 1 if the two items were paired in the same cluster. We're put in the same cluster. And when I resolve the groupings, I'll get something called pi c, the consensus, at time t, because I'm going to iterate. And when I iterate, the part of the algorithm is going to actually put a probabilistic bias on D, such that when you sample D, you get an appropriate subset distribution across the assessors. And we're going to call that presentation a query, and it consists of a number of presentations of elements. And we're going to do that h times for however big the number of assessors are. And it could be 1, or it could be very, very big. Everyone with me? What just happened? Okay, so the way to start is to break it down into 2 pieces. When I go through the solution, the first thing I'm going to tell you is how I can resolve these groupings, or these clusterings. I also say fusing, I also talk about knitting them. And then the second part, I'm going to go through how we can actually iterate here and improve our knowledge until it's stable. And of course, there I want you to have some intuition that we can actually be quite active about choosing these elements. And in that case, it becomes an active learning problem in the machine learning realm, right? Okay, so to resolve the groupings, if I have to do it, and in fact, m is equal to n, then that's a well-known problem in machine learning literature. It's called consensus clustering. There's many different approaches for it. And you know, even if some of those, if some of that data, if m approached n by very close to 90%, there's an expectation maximization algorithm that handles it as a missing label problem. But you know, now we're in this case where n is very, very, very large with respect to m. We're thinking less than 10% of the data. So there's a Bayesian approach in MIPS 2011, the cloud clustering I mentioned before, which doesn't have to worry about any data, uses inference to handle the fact that some data there's no knowledge about in terms of clustering. And our approach is actually coming from sensory science. We're talking about having evaluators look at food products and deciding whether food products are the same. And so in the sensory science, sensory evaluation science community, multidimensional scaling is used. And it would be very interesting. We've got work underway to compare these two. This Bayesian approach could have some vulnerabilities because of the sparseness of the data. And this, of course, has some bias introduced as well, and it would be interesting to compare them. I'm not going to talk about that today. So if I want to resolve subset groupings, I'm going to do it in 3 big steps, and I'm going to show you the details inside. First, I'm going to take that assessor information, which is their co-occurrence matrix. Each one of them gives me for the m elements they clustered. And I'm going to prepare it so that into something called a cross-product matrix, so that I can then aggregate all the cross-product matrices across every assessor for the whole panel of assessors. And I need to do that with some sort of weighting so it reflects what I'm talking about. The fact that I really want that consensus to mean where there's agreement, I get more implications, and where there's outliers, I discount. Okay, and once I can do that aggregation, then there's a very straightforward way of doing consensus clustering from that aggregated cross-product matrix. So let me take you through how we prepare the assessor information. The first thing we do is we have received an m by m matrix from every assessor. And of course, there's a different set of m elements for each assessor. So what I do is I have to register those m elements onto the entire n by n matrix of elements. And I simply, you know, on the co-occurrence matrix, I have a 1 where any 2 elements are placed together. And if I flip that by inverting the 1s and 0s, then I get a distance matrix. Okay? And now a standard step of multidimensional scaling is that I'm going to transform that distance matrix into a cross-product matrix. And what that involves is I'm simply centering the matrix, and I'm normalizing it with the first eigenvector. And what I get out now is an n by n matrix for all the elements, but its real value is not discrete anymore, in 1s and 0s. Okay? So I'm going to call that the cross-product matrix. And now, what have I got? For every panelist, I have a cross-product matrix, and I want to aggregate them. And remember, I want to aggregate them with a weighted aggregation, not something like averaging. That means I want to put emphasis on where they agree. So what I can do is I can actually take the correlation between any one of those cross-product matrices, and I'll do that for everybody. And that gives me another matrix which has the RV, or the correlation coefficients of that test. Okay. What I can then do is I can treat that RV matrix as a new feature space. Right? It's the feature space that tells me about agreement. And I can do PCA on that. And with PCA, I can actually extract with the first two principal components, or the important principal components, a way of mapping this down to a set of weights for each assessor. And details I can show you offline, but the idea is that I want to weight the panelists who agree with each other more, their cross-product matrix, than the ones who are outliers. Right? And so you're going to see that in the next step. This is my cross-correlation, my correlation testing against everyone, which gives me an RV. And then this is the PCA, and then the flattening into 1D space, which gives weights to every panelist, every assessor. And here you just see that, I've created what I would call the global cross-product matrix, and that's just the sum of everybody's cross-product matrix with their own particular weight that I got from that previous step. And next step I have to do, if you recall, is I have to take this global consensus, this sort of consensus cross-product matrix, and I need to turn it into consensus clustering. And that's very standard. I'll just do a spectral clustering method. I'm going to run it through PCA and run it through any your favorite clustering algorithm with the principal components, and I get back now this fused consensus clustering. Okay, so I've given you the solution to the first step in the problem. That's a quick review of it. But my next challenge is to figure out logic for that iteration so that I can actually know that I've achieved a stable consensus clustering. And that's going to mean two things. I need to form the next set of presentations. And I want to do that so that I converge as quickly as possible with this consensus that is sensitive to the agreement. And of course, I need to know when I'm going to stop and when I'm stable. And the halting criteria is very easy. What I can do is use mutual information. I can take the co-occurrence matrix that represents the consensus clustering at time t, and I can compare it to the one in the previous step. And if the mutual information is very high, then it's not changing much. So under some threshold, I'm going to decide how to change that. Now, of course, my algorithm is sensitive to that epsilon, but I'll show you that it's very consistent. This notion of stability with mutual information is very consistent with convergence of accuracy with respect to the ground truth clustering. So let's go back to thinking about the problem of selecting the next set of elements to see what happens, right? And we're going to call this, I'm going to refer to this as active learning because, with adaptive sampling. And that's because if you're looking down here, I'm going to basically form a distribution on the original data. And once I'm going to form a distribution, I'm going to use that distribution to sample the data set D to come up with these queries that I send back to the assessors. And I need two pieces of information. And in this talk, I'm going to tell you about information that's pairwise. It's just telling me whether two elements in the data set have been clustered together, they've been put in the same cluster or not. Now, that's not all the information I have, but today I'm just talking about that. Okay? And if I want to use that information, I'll break it down into two pieces of data, two things. A C, which is my pairwise co-occurrence matrix, which tells me for any two elements if they actually got clustered together, how many times. And then my pairwise presentation matrix, which is telling me just how many times I actually gave them to an assessor together, right? Because they may not have actually been presented a large number of times. So with that information, the first two strategies I can tell you about are very basic. One is just random. I don't do anything that I wasn't doing before. And that can be our baseline. But a little bit smarter, but still naive strategy, is what we can do is we can just go to the presentation matrix and we see how often did you sample everything, and let's just sample things at an even amount to a uniform level. And to do that, I just have to look at the presentation matrix and map that to a probability distribution and use that probability distribution to sample or to bias the sampling on the data set. And I call that an exploration strategy. But what will probably come to your mind if you spend a little bit of time scratching your head about this is there's more information out there. You know which elements have been placed. You know that elements have been placed pairwise, and you can go back to the data and you can see how many times they were placed together and how many times they were placed apart. And no matter how many times I tell you how many times these guys have actually been sampled, if they've been placed a lot, frequently together, then I'm actually pretty sure that they stay together. But if they've been placed apart, I'm also pretty sure that they're going to consistently be placed apart. What worries me is the ambiguous information I get back for a pair, for a particular pair of elements. That ambiguous information is going to be that sometimes they were together and sometimes they weren't together. So I can very quickly come up with an index over each pairing of elements, which is just the frequency with which something has been paired together given how much it's sampled. Okay, and that number is going to be between 0 and 1. And of course, I really don't want the guys near 0, I don't want the guys near 1. I want to sample, I'm good. I want to sample the ones that are ambiguous, that are near 5. So I just have to map this EI to an index that sort of transforms this number through a Gaussian transformation. And now I get an ambiguity index, which basically says, no, when ambiguity is high, that's what I want to sample, and when ambiguity is low, it's not what I want to sample, and it picks out those elements that are at around 0.5. And if I control the standard deviation of my Gaussian, I can sort of see with what respect I influence whether I pick things at the tail or in the mean, near the mean. Okay, so now I have these strategies, and the problem with exploiting is that I may have seen a pair of elements placed, two different pairs of elements placed together 4 times. With frequency 0.4, but some may have been sampled together 100, and some may have been sampled together, presented together twice. Right? And I really want to spend more time on the ones that I haven't seen very often, even though they look. They're as unambiguous as the other pair. And the other problem I have is that sometimes the data can just be confusing. And I could sit there and I could hammer away at those ambiguous pairs, and they're going to stay ambiguous. It's actually not going to get cleared up because people are going to continue to confuse them, right? So that it sort of indicates I need to mix my exploring and exploiting. And in that case, what I'll do is I'll pick an element, and when I want to pick which element I pair it with for a presentation, I'll form a set of elements which are below some ambiguity index and which are below some frequency of presentation threshold, and I'll probabilistically weight them and use them for the paired product. And then I'll take that new product I picked and I'll iterate. So that will help me sort of negotiate between things that are really ambiguous and still not sampled enough. And if there's none there, then what I'll just do is I'll randomly pick between trying to resolve my ambiguity or sample more. Okay? And let me show you some results. And this latter method is problematic. We're still going to think about it more because there's some parameters there that we're going to be sensitive to. And in these results I'm going to show you, we didn't tune it at all. And that might explain why, for some things, we don't, this mixed method doesn't work as well as just exploiting, right? Exploiting the knowledge you have about item ambiguity. So the first question you can ask is, say I put away the ground truth, but I allow a clustering on all the data. That's what I call complete here. And I fix the number of presentations. I don't worry about stopping my iterations with stability. And I look at the quality of the final consensus with respect to that ground truth. So I look at the mutual information between my final consensus and the ground truth. And I compare that with exploit and explore. And what happens is you see that if I actually get the consensus clustering with my method for clustering all the data, this gap here is representing the noise coming from accessors. This gap here is representing the noise coming from the fact that I have an exploited strategy, and it's only seeing partial amounts of data. And this gap here is the difference between the two methods. Right? And what's really interesting is they cross here. And what's going on here, what's going on here is happening because the difficulty of my problem actually gets harder as I go this way. That's my difficulty index. Sorry about that. But why do these things cross here? It's because I only allowed 500 presentations of the data. It's a very small data set. But because of that, the complete data set couldn't get enough information. But if I was hurrying up and exploiting as I as I looked at formed a consensus, then I actually managed to do better, because the partial bit that was seen was actually intelligently picked instead of randomly picked. Finally, you can compare the strategies. So what we found for just a very small set of data, 100 points, because we're working with sensory evaluation type data, and we looked at giving each panelist 8 products, which is only 8% of the data. And what we did, though, in this comparison is that we allow updating active learning every time we visit one assessor. That's why H is equal to 1. And what you can see is if we're continuously learning without any sort of batch processing of the data, then we see a significant advantage to using exploitation. And the reason the mixed one is probably not working as well is we haven't tuned that balance, those parameters in it. And what you see is that if the data becomes harder, we're not going to get as good an accuracy in terms of mass mutual information with ground truth. And in fact, you start dropping off here and everything starts to look the same. All right? So 2 more slides. We also experimented with just proving to ourselves that if you learn rapidly versus learning in batches, the quality of your answer, the convergence to a stable solution takes longer, but it doesn't change the ranking of the different active learning strategies. And then we actually just looked at our halting criteria. And we just wanted to show that there's a match between the performance improvement and finding stability in the data. So to close, we still have lots of work to do because we just looked at the data at a small scale. But what we'll go away and do is approximate the matrix algebra, because this is all algebraic. Consider different versions of the strategy. And the thing we haven't done is if we haven't looked at whether there's information in the current clustering. Right? We've just looked at pairwise information. It would be very interesting. We've tried some things. Nothing is working better than pairwise. So that's a piece of active research for us.
Thank you.
Thank you for this talk. I did not understand exactly if the different subsets corresponding to the different assessors are overlapping or not.
Yes, they have to be well, they will. Yes, they're overlapping. They have to cover the whole data set.
Yes, but they can overlap between
yes.
two assessors. Okay.
Yes. Yeah, so it's sort of sampling with replacement. And we really have to be a little careful about some of the things we're saying. If you go back to our notes and our details, because you're doing sampling with replacement, you have to be a little bit careful with some of these distributions and the sampling.
Give some thought to how you might approach a multi-label problem. So I imagine if you give people a bunch of images, they're all going to think about, and you don't tell them what the real question is. Some people are going to cluster things by color, or some by animal, dead or alive, whatever, right? So if you're asking them to use their domain knowledge, but you're not telling them essentially a 0-1 label question, how do you discover those sorts of relationships?
The bases? Well, look, in fact, the assumption here is that I don't even know the features, right? I don't actually, I assume that there's some underlying way of characterizing the data that's being used by the assessor, but I don't have that feature information. That would be my assumption here. If I could pair it with that feature information, then I could integrate the feature information later into the results of the clustering. I could basically regress out each cluster, right?
Okay, let's thank our speaker again.
Until I achieve a stable consensus clustering, right? And that's when, regardless of how much more data I present to these assessors in these subsets, the actual consensus clustering I've now adapted and updated is not going to change. Okay, so that's the problem. We call it NIT. We've also called it resolving subset groupings. There's a version of it that appeared at NIT in 2011 called crowd clustering, and that's way sexier. I really wish we picked it. Their particular instance is a little bit different, but you can see that there's different versions of this problem. Even just, for example, I could actually have this data distributed. And if this data to imply there is that that consensus clustering should reflect the agreement amongst the people, and it should discount the outliers in that population. Right? Now, I still have a problem, which is that I have a very large data set, and I really haven't told my assessors very much. I'm allowing them to take all their domain knowledge and their expertise and bring it to bear to decide how to group the data. Then they could actually give me data and I could fuse it into a consensus clustering, but if I rearrange the data and I send it back, I could get a different consensus clustering. So I need to iterate in this problem.
Today's first speaker is OReilly, who's a principal research scientist at MIT Computer Science and AI. She leads the evolutionary design and operation group there. She obtained her PhD from Carleton University, and today's talk is NIT, integrating large-scale partial cognitive analysis of data.
Okay, well, thank you very much for coming to the last session and sticking with me. This work is co-authored with a postdoc in my group, Kellyanne Machinini, who really should be the presenter, but is not. And let me start with an example of the problem. And I'm going to work left to right on this slide. The problem is that no one person can cluster all this data, and we certainly can't ask all the people to cluster the data. So our strategy is going to be to partition the data into overlapping subsets and give a particular subset to each one of our assessors in this targeted demographic who's going to provide the clustering for us. Then we need to collect up all these partial subset groupings or subset clusterings and resolve them and fuse them or knit them together into a clustering that reflects the consensus of this particular population. And when I say reflecting the consensus, what I want, we assume that there's this very, very large data set. I'm showing you here a set of images that perhaps could be on Flickr, but it could just as easily be a multimodal set of text and images and auditory signals, or it could be compiled astronomy observational data. And what we're interested in is deriving a clustering on this very, very large data set where we know what, with respect to the subjective bias of a targeted group of people who are going to look at it and judge and tell us those clusterings. Right? However, our